Hello and welcome to yet another video of Cornerstones of Math. Today we are going to calculate the area of the region enclosed by two hyperbolas, x squared minus y squared over 2 equals 1 and x squared over 2 minus y squared equals negative 1. Alright, let's start with observation. The first important thing to notice is that two given hyperbolas are inverses of each other. That is, we can switch x and y in one equation of the graph to obtain the other one. This means that two hyperbolas are symmetric with respect to line y equals x. In fact, there are more axes of symmetry in this problem setting. Y equals x, y equals minus x, x-axis, and y-axis. Therefore, we can calculate the area of the green enclosed region like this. We calculate the area of this orange-colored region on the first quadrant between blue hyperbola and line y equals x, and then we multiply that area by 8. So in order to calculate this orange area, let us find the coordinates of this intersection point on the first quadrant. This can be done by solving two equations of hyperbola simultaneously. From the equation of blue hyperbola, we have y squared equals x squared over 2 plus 1. Substituting this into the equation of the other hyperbola, x squared minus y squared over 2 equals 1, we have x squared minus 1/2 times x squared over 2 plus 1 equals 1. You can easily solve this for x squared to obtain that x squared equals 2, which gives y squared equals x squared over 2 plus 1, so 2. Therefore, the intersection point on the first quadrant is square root of 2, square root of 2. Of course, you can just use the symmetry, which implies that this intersection point must lie on line y equals x. Hence, you can let k, k as its coordinates and use either of the equations of hyperbolas to determine the value of k. And now the area calculation. From this equation of the hyperbola, we obtain y equals positive square root of x squared over 2 plus 1 for the graph on the first quadrant. Therefore, the area of the orange region is given as integral of square root of x squared over 2 plus 1 minus the line y equals x, where x is from 0 to square root of 2, since this point right here is square root of 2, square root of 2. So we can split this integral into integral of square root of x squared over 2 plus 1 and the integral of x. Here the second term is easy. The antiderivative is 1/2 times x squared, so we have minus 1. However, this first term is rather complicated. There is more than one way to calculate this integral. One such way is to use trigonometric substitution, x equals square root of 2 tangent theta, which leads to the integral of secant cubed. But I am going to use different method here, and if you are curious with the trigonometric substitution method, you can click the link on the top right corner or in the description to check out the related video I made in the past, which deals with similar integral. In this video, I am going to use the hyperbolic substitution. This method comes from the famous property of the hyperbolic function, hyperbolic cosine squared minus hyperbolic sine squared equals 1, where hyperbolic cosine and hyperbolic sine functions are defined as follows. So here, let's make a substitution x equals square root of 2 hyperbolic sine u. From the aforementioned definition of hyperbolic functions, it is easy to show that the derivative of hyperbolic sine is hyperbolic cosine, so we have dx equals square root of 2 hyperbolic cosine u du. Moreover, u equals 0 when x equals 0, and suppose that u is equal to alpha when x is equal to square root of 2. That is, alpha satisfies square root of 2 equals square root of 2 sine hyperbolic alpha. Then we have integral from 0 to alpha square root of 2 hyperbolic sine squared u divided by 2 plus 1 times square root of 2 hyperbolic cosine u du, then minus 1. Here, this inner part is hyperbolic sine squared u plus 1. So by previously mentioned square identity, it is equal to hyperbolic cosine squared u. So we have a constant square root of 2 at the front, integral from 0 to alpha, square root of hyperbolic cosine squared u times hyperbolic cosine u du. And since hyperbolic cosine function is positive everywhere, we have square root of 2 integral, just hyperbolic cosine u times hyperbolic cosine u du. So we have square root of 2 integral hyperbolic cosine squared u du minus 1. Here we can integrate hyperbolic cosine squared by applying the half argument formula of the hyperbolic cosine, which looks quite similar to the half angle formula of trigonometric function. Then we have square root of 2 divided by 2 right here, then integral 1 plus hyperbolic cosine 2u du. The integral of hyperbolic function works similarly to that of trigonometric function. So we have square root of 2 divided by 2, then antiderivative u plus the antiderivative of hyperbolic cosine 2u is 1/2 times hyperbolic sine 2u, which leads to square root of 2 over 2 alpha plus square root of 2 over 4 hyperbolic sine 2 alpha minus 1. And as for this hyperbolic sine 2 alpha, we apply this double argument formula for hyperbolic sine, which gives square root of 2 over 2 alpha plus square root of 2 over 2 hyperbolic sine alpha hyperbolic cosine alpha minus 1. Here, alpha is the value of u when x equals square root of 2, so it satisfies square root of 2 equals square root of 2 hyperbolic sine alpha, or hyperbolic sine alpha equals 1. Then from hyperbolic cosine squared minus hyperbolic sine squared equals 1, and that hyperbolic cosine alpha is positive, hyperbolic cosine alpha is given as square root of 1 plus hyperbolic sine squared alpha, so square root of 1 plus 1 squared, so square root of 2. Therefore, the area of the orange region is square root of 2 over 2 alpha plus square root of 2 over 2 times 1 times square root of 2 minus 1. And you can easily notice that these two terms cancel out, so it is just square root of 2 over 2 alpha. But this value is the area of the orange region only, which is 1/8 of the entire enclosed area. Therefore, the entire enclosed area A is given as 8 times square root of 2 over 2 alpha, so it is 4 square root of 2 alpha. And from hyperbolic sine square alpha equals 1, we can write alpha equals inverse hyperbolic sine of 1. So we can write area A is equal to 4 square root of 2 times inverse hyperbolic sine of 1. This expression is good enough since inverse hyperbolic sine is a well-known function, but we can actually express inverse hyperbolic sine of 1 with other elementary functions, owing to the fact that we can express inverse hyperbolic sine x using other elementary functions. If y equals inverse hyperbolic sine x, then x is equal to hyperbolic sine y, meaning that x equals e to the power of y minus e to the power of minus y over 2, or e to the power of y minus 2x minus e to the power of minus y equals 0, or if you multiply e to the power of y, we have e to the power of 2y minus 2x e to the power of y minus 1 equals 0. Therefore, using the quadratic formula, we obtain e to the power of y equals x plus square root of 1 plus x squared, taking plus sign here because e to the power of y must be positive. This means that y which is the inverse hyperbolic sine function, can be also expressed as ln x plus square root of 1 plus x squared. Therefore, alpha, which is inverse hyperbolic sine 1, is equal to ln 1 plus square root of 1 plus 1 squared, so ln 1 plus square root of 2. This means that area A is equal to 4 square root of 2 times ln 1 plus square root of 2. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.